Okay. Hello everybody, I'm Richard and I have 85 slides to go through in 45 minutes, so I'm going to start punctually. Thank you. I was given the task of talking on how SQLite database engines work in general, which is a daunting task in as much that I don't really know. I only know how SQLite works, which is the one I wrote, and about the others I'm pretty much guessing based on advice from Jim and Ann and Bruce and Brian and others. But I'm going to give you my best go, and we're going to try and go through this. The target audience here is people who use SQL in their daily work, and they've been using it for years. And what I've found is that when I go out and get talks to people, is there's a lot of people that know so much about SQL, but the database engine itself is a black box to them. They don't understand what is going on internally. They know they need to create indices. They don't really understand what the indices are doing and why they're important. And a lot of people I've talked to, they don't even really understand that SQL is a programming language. So I'm going to go over all of these concepts. And even if you already know all this stuff, hopefully some of the diagrams I show you will give you a new insight, a new way of looking at things, and help you to better understand and be able to use SQL better. And I'm hoping that the experts here will correct me when I go wrong. Now, I do have a lot of slides, so pay attention, fasten your seatbelts, and hang with me. We're going to be drinking from a fire hose. Key concepts. The SQL, people say it's a query language. It's really a programming language. It's a peculiar programming language, though, because instead of describing what you're going to do, like you would do in C, or instead of describing how you're going to do it, you tell it what you want to do, and then you let the compiler figure out how to go about doing it. So really, an SQL database engine consists of two parts. There's a compiler that takes your program, which is a statement of SQL, and compiles it down into procedures that are going to be run, and then there's a virtual machine underneath that actually runs the procedures. So for example, if you have a simple query like select everything from table 1, this might get translated into a program that would look something like this. You would open the database file that contains the table, and you rewind to the beginning of the file, and then you'd start looping through the file, reading out columns and returning them to the user until you reach the end of the file, and then you would close the file. And you say, well, that's really simple. I could have done that myself in a few lines of C code. And you're probably right. But the usefulness of SQL comes into play when you get more complex queries. And there are, perhaps a few thousand ways you might have implemented something like this. And you really don't want to take the time to write the several thousand lines of C code that would have taken to do this manually, nor do you want to have to worry about all the different algorithms that you might employ and then get close to delivery and discover that you want to rewrite it with a different algorithm and spend a couple of weeks redoing it. So the beauty of SQL is it does this for you automatically. A few lines of SQL will automatically generate a ton of procedural code for you, and simply by adding an index to your schema, you can completely select it. You can select a completely different set of algorithms to use. The task of selecting which algorithm to use to access your data is the job of the query optimizer. And so that's where all the voodoo is happening. So here is kind of a diagram that's showing you the ins and outs of an SQL database engine. You've got some SQL statements that are going in, and this goes into a compiler. It compiles SQL into some procedures, and that generates a prepared statement. The prepared statement is really a computer program and sort of a virtual language, and then this gets sent into the execution engine, which actually goes and does all the actual querying and returns the results to you. So the first part there, the front half, is the compiler, and that's basically the same techniques that were developed in the 70s and are well documented in the Dragon book. There's nothing really extra new going on there. And then in the middle, the prepared statement is the program that's going to run. Now, I think in all of the database engines that are represented by developers here, except for mine, SQLite, everybody uses for the prepared statement structure in C, or a tree of structures. Is there corrections on this, Jim? Are there corrections on that? Now, SQLite actually generates bytecode, which more closely resembles what you would find in Java or USB P code for Pascal, or Parrot. it generates bytecode, and you can actually get kind of an assembly language listing of this bytecode when you use explain. But you know what? It's the same idea behind them all. I actually
clarify.
Sure.
When I said I use a tree of structures, I'm speaking Firebird, Falcon, Nimbus, not MySQL. MySQL uses a forest of good flags.
Okay. Well, yeah. Now there was, and I can't remember the name, but there was a database engine at one point that actually generated native assembly language or native machine code for 8086. And so, yeah, that was kind of weird because you could do that, but it doesn't really buy you anything in speed, and it causes portability problems. So anyway, you get your prepared statement, and you send it into a virtual machine. So here's the architecture of SQLite, and I'm showing you this just to kind of give you some more detailed views of things. The first three things up on the top of the SQLite structure diagram, well, that's just the Dragon book, right? That's the compiler and stuff. I'm not really going to say any more about that other than to tell you that it's equivalent to my original diagram. And then the bottom part is the part that runs the program. And I want to kind of break that out a little bit. Now in SQLite, the virtual machine, because SQLite uses bytecode, the virtual machine consists of a big loop with a switch statement, and it switches on the opcodes, and it runs the various opcodes in turn. Now, as I said, most other database engines actually use a structure or a tree of structures, and when their virtual machine just actually walks the structures. But it varies from place to place. Now, SQLite uses exclusively now underneath the virtual machine is your layer that's going to be doing the database access. In SQLite, we're only doing B trees because SQLite is supposed to be small. Most of the other big engines, you have B trees, and you have hash tables, and you have R trees, and other schemes. I mean, there's often a selection of things that you can do here. Let's just, for right now, let's just assume that they're going to be B trees. All the same principles apply. B trees are well documented by Knuth. In my volume of Knuth, it's volume 2, but he's renumbered the volumes now. It's now volume 3, searching and sorting. And then below that, there's a layer that's going to handle your cache of your database and the atomic commit stuff. And SQLite has an OS portability layer because it has to run on lots of strange things like iPods and cell phones, and where the operating system is not Unix. And so there needs to be some portability factor in there. Let me go back and point out that in like MySQL, the bottom three layers here, the B tree, the pager, and the OS, that whole assembly is what gets plugged in and out when you use a different backend for MySQL. And there's what, 55 of those now? Who's counting? Then in Postgres, for example, they've got the B tree engine, they've got hashing, they've got R tree, maybe there's some others. Firebird, what does it use?
B tree.
Is 100% B tree for everything? What about for the main tables? Does it just use file offsets, or does it use B trees to find entries there? Well, I'll clarify that in a second. Okay, so when you create a table in SQL, you generally get something on disk that looks approximately like this. Here I've got a table with 3 columns, and in the database file itself, you've got the data stored in the 3 columns shown in blue, but you've also got a unique key on every row in the database file. Now I'm calling it row ID here because that's what SQLite uses. Postgres calls it a CTID, I think, a CTID. What is it in Firebird?
A record number.
A record number. And SQLite exposes the row ID. You can always use it, you can set it. And in fact, in SQLite, the row IDs are numbered sequentially 1, 2, 3, 4, 5. In this example, I've put non-sequential numbers to kind of give you the idea that this might be just a file offset to find the record ID. But it varies from system to system, but the concept is generally always there. Now, so we've got the key on the left and the data on the right. The key has to be unique. The data doesn't necessarily have to be. The key has to be unique. So if you do a query like this, where you want to get the price of peaches, one way to find that answer is to start at the beginning of the table, loop through record by record, looking for cases where the column fruit is equal to peach. And then when you find one, it just goes over and pulls the unit price and spits it out. That's a full table scan. If your table only has 7 entries in it, this is fine. You know, actually, if your table only has 7 entries, anything you do is going to be plenty fast. But if you have 700 million entries, this is going to take longer, and so this doesn't really work so well. Well, I know one way you could do it faster, at least in SQLite, is that you could query by row ID. So in SQLite, you could say, select the unit price from the table where the row ID is equal to 93. And in that case, SQLite would do a binary search, find the row, and spit the thing out. And it could do that very quickly, regardless of how many numbers. Now, on other database engines, which would use a file offset, it didn't even have to do the binary search. You could just seek immediately to that row and spit the number out for you. Is the row ID accessible in Firebird? I don't know.
The row ID is accessible. It's called an RDB key.
Yeah.
When you're actually referencing it.
Can you use it in a query this way?
It's set by the system. You could use it in a query. It's not guaranteed stable across transactions.
Okay, so it can shift across transactions in Firebird, so it probably would not be a good idea to do this query there.
Actually, it is stable, but we say it's not.
What I mean is that it can be reused if the record is deleted and replaced.
Right, yeah.
And
but you could do this.
It actually is. You can do it by that number. That number represents the
file number, the offset in the file, and the record.
It's much more complicated than an offset in a file. It's a 2-level index.
Yeah, so it's kind of complicated. But the really key point is here, nobody really cares what the unit price is for row ID 93. I mean, that is not something that an end user cares about. You want to know what the unit price is for peaches. So for this, we need an index. And an index typically looks something like this thing over here on the left, index 1, where we're indexing the fruit column. And so what happens is it builds kind of a separate table, often in a separate file, and it puts all of the values for fruit there in order. And it also records their row ID. So the key point to remember, there's a one-to-one mapping between entries in the index and the main table, and the thing that you're indexing becomes the first column of the table. And you also add this extra column, which is the row ID. And then the combination of the thing you're indexing and the row ID has to be unique. And that's never a problem because the row ID is always going to be unique. So now what happens when you want to get the unit price where fruit is equal to peach is that you can do a binary search to find the entry where fruit is equal to peach. And then you can look up the row, and that gives you the row ID. And once you have the row ID, you can use the row ID to look into your main table to figure out what the unit price is. And so this is the basic idea behind indexing. And this works even if you have multiple terms in your where clause. So here's an example as we want to find the unit price of all California oranges. We want to find the unit price of California oranges. All right, so we've got this table on fruit, and so we could use that first term of the where clause, fruit equals orange. And so we know that fruit has to be equal to orange. We'll use their table and we'll do a binary search for orange in our index. And there's actually 2 entries where the fruit is equal to orange. And then we'll take each one of these row IDs and we'll use that to look up into our main table. And the first one is row ID 0, so it looks that up in the main table and says, oh, well, the Gronian is now Florida, and that doesn't work. So we have to kind of reject that path. But on the second one, it is Californian, so we can output the result. And so this is how you would do a lookup if you had 2 terms in the where clause. Of course, you might have also had another index called, say, index 2 on the Gronian column. And it works just like index 1, except for here, instead of being an index on fruit, it's an index on Gronian. And now we have the Gronian field sorted, and we could use that with exactly the same query, and it would use the Gronian to look up their 2 entries in the Gronian index. But once again, we're getting 2 entries out, and one of them really isn't successful. It blocks when it goes down to the main table, and you're only getting 1 result. So this suggests, well, maybe we'll create an index with 2 columns now. So let's talk about a multi-column index and see how that works. I feel like I'm going really, really fast. What time is it?
10 after.
Yeah, I'm going to finish early. That's okay, we can ask questions. I shouldn't have deleted quite so many slides this morning when I was pruning my talk. So here's index, this should say index 3, that's an error on the slide. We've got 2 columns on the index now, and the way this works is it just creates an index where it has the 2 columns that you've named in the order that you've named them. And we sort primarily by the first column, and then in the case of a tie, we use the second column to sort. In this sample set, the only case where we have a tie is on oranges, and there we see that California comes first. So now, when we want to find the unit price for California oranges, we can do a binary search on the 2-column index, find the one entry where they both match, use the row ID there to go look in the main table, and from the main table, pull out the unit price. And so this is a little bit faster than the other approach. Now, I've talked about 4 ways to get the answer on that one query so far. There's a few more coming up. Let's just do a quick review though. We can do a full table scan, which works great on a 7-table entry, but a 7-entry table, but is a little bit slow on a 700 million entry table. And we could use our single column index on one term of our where clause. And that works okay, but then we're still pulling in some rows and having to check them in cases where the other term of the where clause didn't work out. Or we could do a single column index on the other term of the where clause, and that also works, but once again, we're failing some cases where the other term of our where clause didn't work out. Or we could use a 2-column index on both terms of the where clause, and you can get right to the answer you need right away, and that is generally a little bit faster. Well, what would happen, do you suppose, if we had a 3-column index? Here I've got an index for fruit grown in and unit price. And as you've seen before, the index is built just by copying the values of the individual fields into the index in sorted order, sorted according to the order that the indexes appear. Now in this case, if we do our query, here's example number 5. It does the binary search for oranges in California, but it doesn't have to do the additional lookup over into the main table in order to get the data. The data is sitting right there in the index, and it can output it straight away. Now, if you were at the last talk in this room, Greg mentioned that this doesn't work for Postgres, because in Postgres, the visibility information is in the main table. And so you don't know if this row is visible or not. You still have to go do a lookup in the main table in order to get the visibility information. And I guess is Greg still here? Yeah, there you are. So I guess when you were talking about you're moving toward heavy indices, you would put the visibility information in the index, and then Postgres would be able to do this.
Right.
That's what you were saying.
For what it's worth, Firebird's like Postgres. The Falcon engine in MySQL is like current Postgres, Firebird. Maria has heavy indexes by default.
Okay, cool. Now I understand that the reason Falcon won't do this, or at least Brian was telling me the reason Falcon won't do this, is that the indices are like prefix indices. They don't contain a complete copy of the actual data.
No.
They're
prefix compressed and suffix.
They're prefix compressed. You can still construct the original
That's
data.
not the issue. The issue is that
It's the MVCC stuff that you have to get at.
Yep.
Okay. So now, it's useful to think about these wide indices all the same though. And notice that, for example, you don't have to use every column in the index. Here we're just want to get the unit price for oranges. And I made this slide this morning before coffee, and I see immediately that there's a mistake in it, in that it should actually be pulling out 2 rows instead of 1, but you kind of get the idea. So this also works. You could do that sort of thing. You could also do a thing here where you're selecting, say, the middle column of the index, and it's using the further column out to just do some additional pruning. So really, we're only using the fruit equals orange term of the where clause to do our lookup. And then we're having to scan 2 entries. and then we're also filtering based on unit price, but we can do the filtering right there in the index. We don't have to do this additional lookup over into the main table. And in fact, Postgres, I'm told by Bruce, will do this very thing, because to do the filtering on that first row of California oranges there, because they're too expensive, you don't need MVCC information in order to pull that off. It's able to do that filtering and therefore eliminate one trip over to the main table. Does Firebird do that?
No. Yes?
There is disagreement amongst the experts.
Okay. If you have to skip the middle time,
I'll use the first part.
you use the first part. That gets you 2 records.
It's your idea.
Okay, does it look up Orange, California? Does it look up both oranges in the data table? Okay, so I was right.
We'll do some checking on Firebird to figure out exactly what it does in a little bit. So now we talked a little bit about searching. Yes, Jim?
I'm tossing what our idea here. Firebird and the internal Falcon engine of MySQL, maybe in the future, has another way of doing this type of query. And that is...
I've got number 6 coming up. Do you want to hold the question?
We'll hold it.
But for the time being, I showed you a picture of Knuth's, tone here earlier, and the title of this volume is actually Searching and Sorting, and that's not really a coincidence, because searching and sorting have a lot in common. You kind of think of them as separate things, but they really have a lot in common, and so the indices can come into play here too. Now, if you're just doing a query like this, select star from table, ordered by fruit. One way to do that is to walk through the entire table, pull out all the records, and run them through a sorter. And that works. The sorter can be heavy. The sorter has to store copies of everything. It has to do sorting. And you see, in my world of SQLite, I'm running on cell phones, and sorters take a lot of memory, and cell phones don't have a lot of memory, so this is a very bad problem for cell phones and iPods and stuff. So we'd like to avoid it. Now, you could say select star from table ordered by row ID, and then the query engine would know, hey, it's going to be coming out in row ID order all by itself. I don't need to run it through the sorter, and this makes it run a lot faster. This is linear time rather than in log n. And you could even say select star from tab ordered by row ID decreasing. And this is the same thing. It just starts at the end of the table and moves forward rather than starting at the beginning of the table and moving backward. But, really, nobody really cares anything about ordering things by row ID. That's just not an interesting thing. We really want to order by the fruit. So one way you could do this is to use an index. We could use the index on fruit, and we could start at the beginning of the index and just march down through that index and pull out row IDs, and then for every row ID, we could look up that row in the main table and go and then pull that row out. And so we can go through and walk through and pull out everything in sorted order without having to build a temporary table to store the results. And so it really takes about the same amount of time, but it uses a lot less memory. If you're on Big Iron, you don't care. If you're on a cell phone, this is a huge win. A huge win. And of course, you can do the same thing with a decreasing order by, simply by starting at the end of the table and moving toward the beginning rather than starting at the beginning and moving toward the back. Now, if you happen to have one of these indices that contains all of the terms in it, and you're sorting by the first column of that index, then this gets really simple. You can just start at the beginning of the index and work your way forward, and you know that everything's going to appear in sorted order by fruit. Walk down through the index, pull your values out, send them out to the user. Now, in an MVCC system, unless you've got the heavy indices, you still have to make a little visit over to the main table to check your visibility information. But I guess if you have the visibility, the heavy indices, that's in the index already, and you don't even have to do that. So this is a really fast way of getting an order by. And notice that this same order by works if you're order by decreasing as well. And the same order by works if you're ordering by the first 2 terms of the index. Or if you're ordering by the first 3 terms of the index, it also works. And it works if you're ordering by the first 2 terms decreasing or the first 3 terms decreasing. All of this works. It works great. Now, but this doesn't work. If you put the first term decreasing and the second descending and the first one ascending, that doesn't work. Now, you can declare your index such that it, when you're saying create index, you can say create index, and you can put the descending and ascending keywords after each term of the index. And if you declared it to be descending, ascending, then this would work. But if you declared your index to both be ascending, which is the default, then this wouldn't work because things would appear out of order. The other thing that wouldn't work is that if you skip a column in your index, here we're trying to order by fruit and unit price, and because the Gronian is in between there, things would not come out in the right order if we just used our index. So we'd have to use one of the previous order by techniques. And the other thing is that we can't use an index to sort if the thing we're sorting by is a middle term in the index. It's got to be the leftmost term in the index in order for any of this to work. Now, there are some other tricks you can play, though. So here we've got a case where we want to get some stuff out of the table, and we're restricting our search to where fruit is equal to orange, but we're ordered by the state that it's grown in. Well, I said a minute ago that you can't do order by Gronian and using this particular index, because Gronian is the second column, it's not the leftmost column. But we have constrained the leftmost column to be a particular value. So in this case, it works. Because the leftmost column is constrained, we know that everything is going to come out in the right order naturally, and no sorting has to be done. So here's a kind of a general rule, and we go over this rule once a week or so, I think, on the SQLite mailing list. So hopefully it'll be applicable to other database engine people as well. When you're creating an index to serve a query, you look at your where clause terms, and the where clause terms go first in the index. And then, after that, you put your order by terms. Now, the where clause terms and the order by terms can overlap, but there can't be any gaps. You can't have an extra column in there. And then finally, over here on your result set terms, you want to put all of them in the index too, but there can be gaps, there can be overlaps, it doesn't really matter as long as they're all in the index. Okay. Question in the back.
Yeah, in MySQL, if your query doesn't contain, maybe I have this correct in my thinking inside today. Your key part, only if you're using the first key part does it use that index. Does yours work differently?
Like, is this what you're saying right here?
Yeah. Oh, okay. So it does contain the first part, I'm sorry.
Yeah.
Do you have the same situation?
Yeah, pretty much everybody works the same way here. Yeah. So let's go down and all of the examples I've given to you now had a where clause constructed with ands. What if you put an or in there? Now this is a whole different universe. This is getting usually. The easy way to do it is, of course, a full table scan always works, right? We're asking for all of everything, the unit price of everything that's an orange or that's grown in California. So we could do a full table scan, of course, and that still works. Full table scan is it always works. It's always slow, though, too. So we like to avoid it. The way this normally works when you have an OR is that you've got a separate index on the fruit and a separate index on the Gronian. And so we can look up all of the entries that are grown in California using the index up on top there, and we get their row IDs. And then we look up all the things that are in orange and get their row IDs on the bottom. And so we got 2 sets of row IDs, and then we have to take a union of those 2 sets, and we get the end result is 3 different row IDs, and then we can use those row IDs to go look up what we want in the table. Now there's a couple of ways, or actually there's quite a few different ways that we can do this. Now if you've got, in this particular case, we've got single column indices, and we can stream those row IDs, and the row IDs are coming out of the index in sorted order. So these row IDs are coming out of each index sorted, And so you can merge them together with no temporary storage. Always take the smallest row ID next and merge them together, and you don't have any temporary storage to kind of hold all this stuff together. And that works really, really well if like you're on a cell phone and you don't have any memory. But usually what people do with this is they create something along the lines of a bitmap index, where they, for each of the two, as a transient index, they search each index and they have a bit mask and they set bits, and maybe it's compressed somehow, but they set bits for each entry that actually matches, and then they end up with two bitmaps, and then you just OR them together, and then they walk the bitmap in order to get the entries in the table. What does Firebird do?
Firebird does that.
Does the bitmap thing?
ORs and ANDs.
Does it do the merge thing?
Yeah, it doesn't, I mean, it creates two bitmaps and then,
Creates two bitmaps and does the merge.
Yeah.
Postgres, I'm told, doesn't. It logically kind of does that, but it really doesn't create two bitmaps. It creates one bitmap and then modifies it according to the second index. But same idea. Same idea. Now, the merging thing works okay as long as you have single column indices, but if you had a two-column index on fruit, the row IDs wouldn't come out in the right order, and so you'd have to sort them in order to do the merge. But of course, the bitmap thing still works out okay. Now, this is typically the way you handle where clauses that are done with ORs. But you know what? If that union were turned in, oh, did I press the wrong button? I did. If you turn that union into an intersection, you could also use this approach to do the ANDs that were said. So here's method number 6 of solving our query. That's the ongoing example for this talk. We just look up all instances of California in one index, all instances of orange in the other, and then you pick the entries that they have in common, which in this case is number 204, and that immediately gives you your result. Now, this works, and it works great, but as you can imagine, it's going to be a little bit more work than if you had a two-column index, and it's certainly more work than if you had a covering index like this, where you could just look it up at that point to the table at all. But the advantage is you don't need these multi-column indices, and you can have a smaller set of indices, and you're still going to get reasonable performance. It's not the peak performance, but it still works pretty well. And the other advantage is that you can have really bizarre where clause things like this, kind of arbitrary Boolean expressions. Here I'm asking for the unit price of California oranges and anything grown in North Carolina. And so you can have a tree of intersections and unions on these bitmap indices that'll go in and pull out the data you want just like that. I ran through this really fast. What time is it?
28.
Oh man, I've got 10 minutes for questions. So the key points that I wanted to bring across to you today are that SQL is a programming language. There is a compiler. There is a virtual machine. Indices are not magic. They have to make sense. So often on the SQLite mailing list, I don't know if this is happening on the mailing list for the other database engines or not, people get on and they say, well, I created a bunch of indices, but my queries are still slow. Why? They're not magic. The query still has to make sense. And the other thing is avoid creating too many indices in your schema, because as we've seen, even for a simple query, there were 6 different ways of running the query, and that was for a simple one. I haven't even talked about joins. I cut all of those slides. I haven't talked about subqueries and things like that. I cut all of that. But we had 6 different ways of doing a relatively simple query. When you start talking about joins and other things, the number of combinations of ways to solve this problem really mushrooms really fast. And if you have a lot of indices, that gives the optimizer more things to choose from, and that gives it many more opportunities to make a mistake. So you really should try and keep your indices to a minimum. Those are my slides, and I burned through this a little bit faster than I thought, but we've got time for questions if there are any. Yes, Jim?
One of the things, to fill in what we've been wondering about,
do I need, would the slide help you in any way?
What?
Would going backwards here help you in any way?
Firebird, Falcon, when they do an index retrieval, they scan the index, getting record numbers which are dense, and then setting the bitmap. There are about 3 or 4 reasons it does it. One is the and and or that you talked about, which just works very well. A second is that it doesn't matter in a cell phone, you have a single level store, but in computers, the disk is infinitely slow compared to memory, and if you can access the disk in sequential order, it's vastly faster.
Yeah, so we don't have the sequential order problem in flash memory.
It fetches in bitmap order, which is physical order. And the third is that it vastly simplifies the optimizer because you can use all of the indexes that you've got. You don't have to choose among them.
That's the thought. You're always so
You
what you're
take out
saying
ones
is like on
you take out
Falcon.
ones that are completely redundant, but you use everything you got. You and and or them together, and
So
you end up with.
you're saying Falcon really prefers to do this method over one of these simply because it's really simple to figure out which method you're going to be using when you do it this way.
No.
And your argument is that on server hardware, it's going to be just as fast because because things are streaming off the disk in sequential order, and that's going to be faster than doing random accesses anyway.
My last comment I want to make, and I want to stress this, is that people overestimate the cost of sort. Sort is cheap. You can sort a gazillion records in the time it takes to do one disk access.
On server hardware.
You don't have disks on cell phones.
No, you don't.
If you had a disk on a cell phone, you can still sort a million records, and they're going to take to access the disk. So using the sort to eliminate disk is good.
Okay, good point. Yes, Greg.
In SQLite, can you trick the planner to use the first column if you just want to sort on the second one by saying like where fruit equals fruit, or where fruit is not equal to banana, or?
No, no, you can't, because that sorting trick here, where was that? I've gone past it, haven't I? Oh, here it is. Yeah, no, in fact, if you say where fruit in orange, comma, gray, or something like that, that it's still got to sort it manually, because then that first column is no longer coming out in the right order. Or it's not guaranteed to. I mean, you might get lucky, but there's no guarantee. So it goes ahead and sorts it here, up front.
The SQLite, which does it prefer? Does it prefer the more complex indexes or a bunch of tiny indexes?
Well, as of this very moment, SQLite doesn't do the bitmap indexing. We're putting that in now.
So it prefers larger indexes.
It prefers larger indices. So, yeah, if you give it a where clause with a bunch of with an or in it, it does a full table scan. So, this is one of the problems of fitting in 256 kilobytes. So, but we will by spring that will be remedied and it'll do the full bitmap thing. So, but right now it prefers the other, and it's probably always going to be faster for SQLite because it really is going for the lower end hardware, and the memory really is a factor. At the keynote, I was telling Brian afterwards, he was talking about, we're wasting power. That's never a problem with SQLite because the cell phone and iPod people are constantly screaming at me. They don't care about CPU time. They don't care about memory. What we care about is running the battery down. So anything I can do to save battery power is a plus. Question?
Yeah, SQLite is, I haven't played with it much, a little bit, but it's different. MySQL obviously has a server. How is
SQLite has no server.
It just runs when you use it.
It talks directly to the disk, which is, that has advantages and disadvantages. And in the environment that SQLite is using, is a huge win because if there's no server, you don't need an administrator to start the server, to fix the server when it breaks, etc., etc. The disadvantage is that you can't really do things like MVCC without a server. Because what happens if you get halfway in the middle of well, we'll talk about it later, but I'm convinced you could theoretically do it, but the overhead would be so tall.
Peer-to-peer and multi-VCC.
I want to see how you do it.
Okay.
I want to see how you do it. I don't believe it. I don't believe it.
It was born that way.
Is the client and the program itself all one?
Yes, SQLite is just a pure library. It's really just a translator from SQL into accesses to the disk. Yeah, the slide that I'll give in my next talk, so I'm going to spoil the punchline, is that SQLite is not trying to compete with Postgres and Oracle and MySQL and these others. It's competing with fopen. Okay? That's what we're really trying to replace, not these others. So it's really a very different mission. I've got 5 minutes left. Well, we're on questions anyway, so we're fine. Any other questions? Yes.
I know, I was telling you about 5 minutes.
Okay. Any other questions, or do you have a 5-minute break? Cool.
Okay, back to my question, then you're going to have to add some much more levels of optimization if you have a choice between a complex index and also using bitmaps.
Yeah, what the situation is that the way SQLite is structured, the way we make our money is that we have the SQLite consortium, and that consists of some large companies who use SQLite in their products, and they're sort of mission critical for the products, and so they just kind of give us a little bit of money every year to make sure that we don't go away. And that actually works, and so we've got 3 guys working on it now, and that works really well. But we've recently picked up as one of these companies, Bloomberg, who is using SQLite on Big Iron, and they are, the cell phone people, they really don't want these bitmap indices because they use memory, but the Big Iron people, they want it, and so we're going to have to put it in for them because they're helping to keep the lights on. But we'll probably put it in a way that you can add it as a compile time option, because it is going to make it a little bit bigger and a little bit more complex, and the cell phone people, iPod people, they want to keep it small and simple, so it'll be like an if-def. And you can put this in as an if-def, or you can leave it out according to what you want to do. In truth, though, lately, the cell phone people have been saying, you know what, we can go above your 250 kilobyte limit, go up to 500 kilobytes, we don't care. Because memory is getting cheaper, and so maybe they'll keep it in, I'm not sure. We'll see. Question in the back.
Just a question, where do the bind variables fit into the flow actually store the parsed structure?
Yes, yeah, I had 6 or 7 slides on exactly that question that I cut this morning. In SQLite, well, really in most database engines, you've really got a computer program, and there's these variables in there that get initialized. And when you bind a new value, what you're doing is changing the initializer on that variable. So when you when you compile the program, those initializers are really, in SQLite, they're always initialized to a null. And so you compile the program, you get your program, and all these things are where say variable x equals null, and then you bind a value against that. It changes the program slightly to say x is equal to 1, 2, 3, or whatever number you bound to it. And so the binding is persistent. If you rerun the prepared statement multiple times, unless you change that binding again, it's still 1, 2, 3 every time you run it until you reset it to something different. That would make a lot more sense with a slide, which I deleted. I'm sorry. Does that?
Would you have to regenerate the bytecode?
No, the bytecode is not regenerated. It actually just goes in and changes the bytecode slightly. It doesn't have to insert instructions or anything. It just has to change a constant in there to the new value that you bound to it. That's all it has to do. Other questions? If not, we will adjourn 2 minutes ahead of schedule.